In today's lesson, we're going to be taking a closer look at integration by substitution. There are a few things that can come up in problems that make this a little bit more complicated, and so we're just going to get into those today. But before we get started, let's take a deep breath. And let's begin. I'm sure that I mentioned this in the last lesson, but integration by substitution, I want to be very clear, is not a fix-all for advanced integrals. It's not like any problem that you can't do, okay, yay, integration by substitution is going to fix it. This is just one integration technique out of many, and it's not going to be helpful for every integral. It's going to make some integrals way, way, way worse. Over time, you're going to get an intuition for when it's helpful and when it isn't. Right now, that's not super necessary for us to know because it's the only integration technique we know, but I did want to give you a sense of what it looks like when integration by substitution fails. Right? So in this example, I want us to attempt to use integration by substitution to simplify this integral. So just looking at this one and based on the lesson that we had previously, what do you expect that we would want to try and use as our substitution? Okay. The only thing that seems to make any sense at all here is that we could try using u being x squared. We learned in our previous lesson that our x squared is plugged in, it's composed inside of sine, and that's one of the signs of a good substitution. So the derivative of this du dx would be 2x, and so we'd have du equals 2x dx, and then I could divide that 2x over. So dx is du over 2x. All right, so if I take this now, if I take my original substitution and my dx substitution, and I put them into this integral, I'll now have the integral of the sine of u. And that looks good so far. I mean, I could do the integral of sine u, but I also need to replace the dx. My dx is du over 2x. And right here we notice something that we did not notice in any of our exercises when we practiced the first lesson. Usually when we do a substitution like this, all of these x's cancel out. And this time it doesn't, right? I can certainly use that constant multiple rule to bring the half out front. So I could have half the integral of sine u times 1 over x du. At this point, I don't have any tools that will let me get rid of this other x that's here. And so I have a question that I sort of want to ask you to reflect on. And that question is, what does this example seem to teach us about when integration by substitution isn't useful as an integration technique? So I want you to sort of pause the video, think about that, try and write down a sentence about what do you seem to be seeing here about when integration by substitution isn't useful or when it doesn't work. So what I suspect that you guys came up with was this idea that when all of the x's don't cancel out, it may mean that integration by substitution isn't useful. So again, I really just wanted to give you guys a little bit of a sense of what it looks like when integration by substitution doesn't work. Now, with that said, let's take a look at another one of these, right? I want us now to attempt to use integration by substitution to simplify this integral. I'd ask you, pause the video and at least get through sort of the first few steps in what you think might work as an integration by substitution for this, and then we'll check in, because it turns out that this one we actually can do by integration by substitution. And I want to show you why. So our first step here is to choose our u. So it seems to me that it's going to make sense that we use u equals 2x minus 3, the quantity inside of the parentheses. This means that my du dx is going to be 2. That means du is 2 dx, which means that du over 2 is dx. Okay. Now that I have a substitution for u and I have a substitution for dx, I can take them and put them into this integral. Right. So I'm going to come over here and say, all right, well, this is the integral of x times u to the 4th. And we're kind of hoping that that x is going to cancel out. We've seen it happen lots of times before. Unfortunately, when I substitute in the dx, I have du over 2. And at this point, it may feel like integration by substitution has failed us, just like it did in the previous problem. But something that's different about this problem than the last problem, I don't know that I'm going to go back and sort of show this for the last problem, but this thing that's left as an x, we actually know what x is. We haven't written it down, but take a look at this substitution right here. If this is true, wouldn't it also be true that u plus 3 is 2x? Wouldn't it also be true that 1/2 u plus 3/2 would be x? Like, do you see how I can effectively take this substitution and instead of solving it for u, solve it for x, so that whenever there are any x's left over, I can put this in. Right? So when I do this, I'll now have the integral of 1/2 u plus 3/2 u to the 4th power times du over 2. Okay. Do you see now how this integral actually is all entirely in terms of u? So now the question is, can I, and we're going back a couple days to our basic integration, can I find a way to algebraically manipulate this thing so that I can take this integral? Because right now I can't do this integral. Right now this is two functions multiplied together and we don't have a product rule for integrals. So I would encourage you, now that we've gotten it this far, like if you got this far on your own or if you just followed me, pause the video and make sure that you're comfortable with how to finish taking this integral. So I don't like this 2 that's left over here, so that's a constant multiple. I'm going to bring that out. I'm going to do this as 1/2 the integral, and then I'm going to take this u to the 4th and I'm going to distribute it into both of these. So I have 1/2 u to the 5th plus 3/2 u to the 4th du. And I really want to take a little bit more time here to make sure that I'm careful with all of my steps. We talked in some of the previous lessons about sort of using the addition rule to break this into two separate integrals. When you do that, this half in the front is going to apply to both of them. So you're going to wind up with something like this. Okay? Then I'll use the constant multiple rule again, bring the half out, bring the 3/2 out. So this is now 1/4 the integral of u to the 5th du. And this is 3/4 the integral of u to the 4th du. And at this point, this is a really simple power rule. Right? I'm going to do 1/4 times u to the 6th times the reciprocal of 6 plus the 3/4 that was already there times u to the 5th times the reciprocal of 5 and plus c. And then just like we've done with basically all of these substitution problems we've done so far, at this point I need to go back and put it in terms of my original variable. I want to come back and take this x variable and put it in. So this would be 1/24 2x minus 3 to the 6th plus 3/20 2x minus 3 to the 5th plus c. So what I've tried to show through this example is when you do a substitution and there's still an x left, it doesn't mean that all is lost. It may mean that we just need to go back and figure out how to deal with that leftover x. Now, I think I do want to jump back and look at that previous problem really quickly just to show you why this method would not have saved us there. So this is just going to take us a minute. Let's look at that first problem that we did where it seemed like integration by substitution had failed. Is it possible for me to find a way to replace this x? Well, sure, I could come over to this substitution and say, aha, wait a minute, but x is the square root of u. And so if I plugged that in, I would have 1/2 the integral of sine u times 1 over the square root of u du. And at this point, like, yay, you've successfully replaced all of the x's with u's, but this integral is still terrible. Like, it isn't like the previous one where I could do some algebraic manipulation here to make this something that I can take the integral of. This is still sine times some square root of u in the denominator. There's nothing we can do to take this integral right now. And so that's sort of why just because I can replace the x's doesn't mean I can actually do the thing that's left. So now I want to try and sort of sum up where we are so far, right? We've got this key point. When we use integration by substitution, In some cases, in many cases, all of the original variables will cancel out, but sometimes they don't, right? When some of those original variables are left over, it may mean that the integration has failed, or it may mean that we just need to continue using our substitution. We may need to try a little harder to see if we can figure out how to get all of those x's replaced by u's. Now, I do want you to remember, integration by substitution is not going to work for all integrals. As we get further into this class, you'll need to learn like when the method is failing and when you need to try another technique. Again, right now we don't have any other techniques, but I want to sort of front load that idea. For most all of our problems right now, integration by substitution is going to fix anything we couldn't originally do. And if not, the instructions are going to say, or explain why the integral, is not integrable. So let's briefly review and then update our method for integration by substitution. So these are the exact same 5 numbered steps that we covered in the previous lesson about how to do integration by substitution. All I really added was I added some subpoints under here. You're still taking the derivative of that u and then sort of solving for the dx after taking the derivative. You're still replacing the dx with what you found, and you're still putting in the u's wherever you can. But when we get to the step about simplifying as far as possible, we have this goal of working out the new integral in terms of u. And so I'm putting in here this reminder. If there's any x's that remain in the integrand, think about manipulating your original substitution and then using it again to replace any other x's that are there. And then I sort of put in this step B, if you can't do the resulting integral, try thinking about another substitution or using another integration method. Again, we don't have any yet. And then step 5 still remains the same. After you integrate it in terms of u, make sure to put it back in terms of x. So now I've got a couple of examples for you to try before we go on and talk about one more topic as we talk a little bit about advanced integration by substitution. So I would encourage you here to pause the video and try this one on your own. If you're worried that you're going to pick the wrong u or that you're going to do something wrong along the way, remember you're welcome to sort of pause and unpause as you're working through it. So step number 1, we're supposed to choose our u. Seems like the thing that makes sense is to choose the thing underneath the radical. So u will be 4 minus x. That means that du dx is negative 1. And so when I multiply that dx over, I'll get du is negative dx. And I want to actually solve for dx, so I'm just going to move the negative over. Dx is negative du. So now that I have something to replace for u, and I have a dx that I can substitute in, I'll come back to my original integral. I have the integral of 3x times the square root of, now that I can replace with u, and then my dx, and I'm going to make a little mistake here. I don't want you guys to write this, because it makes it look like this says 3x times the square root of u minus du. And that this dx du thing needs to be multiplied on the end. So this really should be multiplied. And the reason that's valuable is that, like when we think about using the constant multiple rule here, being able to take this 3 and bring it out, being able to take this negative and bring it out as constant multiples are valuable. So I'm actually going to do that right now. I'm going to pull out this negative 3, and I have the integral of x times the square root of u du. And here I am again. I've got this extra x left over, so hopefully what you noticed is that we can take our original substitution and solve it for x. I can get u minus 4 equals negative x, and that means that x could be 4 minus u. So I can take that and plug that back in where I see that leftover x. Negative 3 times the integral of 4 minus u times the square root of u du. And at this point, I want to be really clear. I still can't take this integral, but I can do an algebraic manipulation. I can manipulate the inside of this so that it is ready for me to take the integral. So this will now be negative 3 times the integral of 4, and I'm going to write this as u to the 1/2 because I can see it coming that I'm going to want to use the power rule here. And here I'll have u to the 3/2 power, which I got by thinking about this being a u to the first and this other one over here being a u to the 1/2 power, and I just added those powers together. Final steps I want to do here are to use my rules of integration to break this into integrals and use the constant multiple rule to bring things out. So I'm going to have negative 3 times the integral of 4u to the 1/2 du. And then here I'm going to have minus 3 times the integral of negative u. So, so maybe we do this. Maybe we even leave that negative in there. And now when I do my constant multiple rule, I'll sort of bring those things out. So this is negative 12 u to the 1/2 du plus 3 integral u to the 3/2 du. And now finally, these things are in their nice, simple, easy forms, and I can do those integrals. Negative 12 u to the 3/2 times the reciprocal plus 3 u to the 5/2 times its reciprocal plus c. And then you guys remember what our very, very last step is? Our very last step here is that I'm supposed to take my original substitution and use it to rewrite this in terms of x. So this will be, let's see, these reduce down to 4. So this will be negative 8, 4 minus x to the 3/2 power, plus 6/5, 4 minus x to the 5/2 power, plus c. So I hope that you guys can see that, yeah, these can get a little bit more complicated than the ones that we were initially doing, but even when there are x's left over, this process is manageable. As we look back at this looks like a lot of work, but this was really me meticulously showing every step along the way. As you guys get more comfortable with this, you'll find that some of these steps that we do along the way are things that you can combine together. So we've got one more example of one of these integration by substitution problems where we need to work in another x, and then we'll move to the last phase of the lesson. So here, our u is going to be x plus 2, which actually makes this part really easy. Du dx then is 1, which means du is just dx. Okay, so from there, I'm going to go back and rewrite my original integral. So in the numerator, we've got x squared. In the denominator, the square root of u, and then my dx just turns into du. We notice again that we've got this x squared in the numerator, so we deal with that as we have before. We take a moment to think about our substitution. That substitution means that u minus 2 is equal to x. So we can take that and put it up here. Some people, by the way, like to sort of recognize, hey, I'm going to need to know what x squared is, so let's just figure that out over here, like before bringing it into the integral. You can bring it into the integral and square it, or you can work it out on the side. I just sort of wanted to point out that you could certainly do this over on the side. So x squared is u squared minus 4u plus 4. So now you could take that and put it back over here. We could have u squared minus 4u plus 4 all over u. All over the square root of u. And then from here, this again is one of those fairly straightforward problems that we had seen from our previous lessons. Algebraic manipulation is going to let me break this into 3 separate fractions. So I'll have the integral of u squared over square root of u minus 4u over the square root of u plus 4 over the square root of u. And now I'll use the addition subtraction rule to split this into 3 separate integrals. I'll have the integral of u to the 3/2 du. I'm just sort of skipping the step here of dealing with these powers. In the next one, I'm going to have minus 4 times the integral of u to the 1/2 du. And finally, plus 4 integral of u to the negative 1/2 du. So what I did here is I sort of just did the addition subtraction rule. I also did the constant multiple rule to bring those constants out, and we simplified the powers that were left inside. We increase the power by 1, multiply by the reciprocal, minus 4 times, do it again, u to the 3/2, that's increasing by 1 and multiplying by the reciprocal. And then in the last one, 4, the power goes up to positive 1/2, and we multiply by the reciprocal, 2 over 1, and we put our plus c on the end. Last thing we're going to do is simplify those coefficients and then plug the x plus 2 back in. So I'm going to do those things at the same time just so I don't run out of space here. So this will be 2/5 x plus 2 to the 5/2 minus 8/3 x plus 2 to the 3/2 plus 8 times x plus 2 to the 1/2 plus c. So that's going to be the end of our sort of simple examples of this. We're going to move into one last component at the end of this video. So the last idea that I want to cover in this lesson is about definite integrals. And it's worth noting, it's important for you to know that when you're doing integration by substitution on definite integrals, the bounds of integration have to be changed. Okay. Before we do that, I do want to sort of remind you briefly about definite integrals. So first, the definition. A definite integral is basically an integral that has bounds of integration. In these integrals, you don't put a plus c on the end, like on an antiderivative, and your answer is generally going to be a number, and that number usually represents the signed net area between the curve and the x-axis. This was something that we learned last year, but again, you might have forgotten about it, so we'll review it briefly here. The way that this process works is we do the antiderivative, and I made this one really simple. The antiderivative of sine is negative cosine. So we have negative cosine x, and then instead of putting plus c, I'm going to move these bounds of integration to the end. And what we do with these things is we first evaluate your antiderivative for the top one, minus, and then evaluate your antiderivative for the bottom one. And we subtract them from one another. Okay, so the cosine of pi over 2 is 0, so this is 0 minus a negative, and then the cosine of pi over 6, on the unit circle, pi over 6 is this one over here. Cosine is the x value, and that's a large value, so the square root of 3 over 2. So this answer is the positive square root of 3 over 2. I mentioned that this is the signed net area between the curve and the x-axis, so it just means that if you imagined the sine curve between pi over 6 and pi over 2, the area between sine and the x-axis is right there. This integral is basically telling us that the area of that thing, the net area, is positive root 3 over 2. If I had found an area that was under the curve, it would have been negative, and if I had asked you to do this integral from 0 to 2 pi, that integral would actually have turned out to be 0, because the positive area and the negative area effectively cancel one another out. Again, this video is not actually going into all those details. I just want to remind you briefly about definite integrals so we can talk about what happens when we do integration by substitution on a definite integral. All right, so here's the deal. When you evaluate a definite integral that takes integration by substitution, the really important part is you're changing the variable. And so because you're changing the variable, you also have to change the bounds of integration, and you do it by using that substitution. Okay, so I'm going to go ahead and go through one of these examples fairly quickly for you, and then I'll have one last one at the end that you can do. So we're going to start this problem, and I'm telling you what the substitution is. So I'm going to start by saying, all right, well, I know that my u is supposed to be 1 plus sine theta. That means that du d theta, and I know we usually write du dx because this is usually an x over here, but in this case it's theta, so fine, du d theta is cosine theta, and then just as we've done before, I'm going to do du equals cosine theta d theta, and then du over cosine theta is d theta. So now I come back to the problem, and I can write this as the integral of cosine theta over u, and then my d theta was du over cosine theta. And so yay, these things cancel out, but this is awkward. I have an integral up here with bounds, and then I have one suddenly here that doesn't have bounds, but I don't want to put the same bounds on it because it's a different variable, right? So what I'm going to do at this point is I'm effectively going to say, well, let's see here. In my original integral, theta was supposed to be pi over 2. Well, let's find out what u is in that case. U would be 1 plus sine pi over 2. And you may be wondering where I got that from. I'm just using the substitution I did here. I'm saying if theta is pi over 2, then when I put that pi over 2 in, I should be able to find out what u is that sort of corresponds to that one. And so when I work this out, I find out that this u value is 1 plus 1, which is 2. Yay! Similarly, and so that means that I can put 2 as my upper bound, because I'm replacing the pi over 2, which was a theta variable, with 2, which is a u variable. And we're going to do it again here. If I have 0 here, this will be u equals 1 plus the sine of 0. Well, that means 1 plus 0, which is 1. So my bottom bound has turned into 1. So now I'm just going to rewrite this integral so we can clearly see what's happening. The integral from 1 to 2 of 1 over u du. Well, that one's really easy. This integral is just the natural log of the absolute value of u, which we evaluate from 1 to 2. So this is going to be the natural log of the absolute value of 2 minus the natural log of the absolute value of 1. The natural log of 1 is 0, and so my answer here is just natural log 2. So definite integrals are really not any harder for us to do. All we need to do is remember that we need to change the bounds. If you leave the bounds alone, you're going to get a wrong answer when you get here. By the way, quick comment. The reason I didn't write the absolute values here anymore is that I don't need to. 2's positive, and so I don't need to say, ooh, make sure you take the absolute value of that number that's already positive. So that's why I left that out. All right, so I've got one final example of a problem that takes integration by substitution that's also a definite integral, and so I'd like you to pause the video and try this one on your own. If you're feeling anxious about whether you're going to get the u substitution right, feel free to check in, but then after that I would like you to try the process on your own. So the u that we're going to use here is 2 minus x, and that means that du dx is negative 1, which means that du is negative dx, which means that negative du is positive dx. So I've got these two substitutions that I'm going to use. When I go to plug them in over here, I'm going to have the integral, and I'm not going to write the bounds because I know I'm changing this here. I'm going to have the integral of x over u squared times negative du. And I'm noticing right here that I'm not quite done dealing with the x. I've still got this x here. So let's step down here for a moment and look at what's going to happen with that. We can see here that u minus 2 is negative x, and that means that x is 2 minus u. Okay, so I'm going to come back here, and I'm going to put 2 minus u up here, u on the bottom. And this du, I'd really like to just put the du here, and constant multiple will bring the negative out there. One thing that I'm missing here now, though, is the bounds, so I'm going to go back and figure out those bounds, right? We previously had an x bound of 1, so that means that x was 1, and so that means that u is supposed to be 2 minus 1. Remember, I'm taking that by using the substitution again. Oh, so that bound actually stays the same. So my top bound is still 1. Now what about the other bound? When x is 0, it means that I get u equals 2 minus 0, which is 2, and so my bottom bound is 2. Now, you may or may not have seen problems where the upper and lower bounds are smaller than, like where the top bound is smaller than the bottom bound. This is the thing that can happen. If you forgot about what that means, it's something that we'll review again. We'll come back to it at some point. I'm not going to get into the meaning of that right now. We're just going to work through finishing this problem. Last thing I need to do now is just work this integral out. So I'm going to have the negative integral from 2 to 1 of an algebraic manipulation says that, let's multiply this thing out. In the numerator, I'm going to have 4 minus 4u plus u squared. That's just me sort of foiling that thing out, divided by u squared du. And now I'm sort of thinking, all right, this is one of those problems where I need to split it into multiple pieces. So this is going to be negative integral from 2 to 1 of 4 u to the negative 2. That's this first one. And then minus 4 over u. That's this middle setup. And then at the end, I'm going to have plus 1 du. And I skipped a few steps there. If you're not comfortable with that, please make sure that you show that. But I sort of set these things up here so that I'd be able to take the integrals of them. And then for each one of these things, we're going to walk through and actually do that integral. So I do need to take care. I do need to be careful with a few things here as we're working through this. I want to use these bounds, the 1 and the 2, on this entire thing. So what I'm going to do now is I'm going to sort of focus on doing this integral, and we'll put the bounds on at the end of the whole thing. So first I'm going to sort of do the addition subtraction rule and the constant multiple rule to move some things around here. This first integral piece is going to be negative 4 times the integral of u to the negative 2 du. The next one, there's negative and a minus here, so this is plus 4 times the integral of 1 over u du. That's this one. And then for the last one here, I'm just going to have minus the integral of, effectively 1 du. Okay, all of these are from 2 to 1. All of these are from 2 to 1. But what I'm going to do is I'm going to sort of apply all the bounds at the same time at the end. So this first one here, I'm going to have negative 4 u to the negative 1 times the reciprocal of negative 1, which is negative 1. And then I'm going to have plus 4 natural log absolute value of u. And then finally I'm going to have minus u at the end. And instead of putting a plus c on the end, I'm going to say all of this is being evaluated from 2 to 1. Okay? So you see what I'm doing there is I'm effectively doing each of these integrals and then not putting in 2 and 1 and 2 and 1 and 2 and 1, but saying let's take the entire thing and put in 2 and 1 for it. This first one, actually I want to simplify this just a bit more. This is going to be positive 4 over u plus 4 natural log absolute value of u minus u evaluated from 2 up to 1. Remember, you're always using the top bound first. So now as I go back and evaluate with these things, I get 4 over 1 plus 4 natural log 1 minus 1. All of that minus, and now I evaluate with 2. 4 over 2 plus 4 natural log 2 minus 2. All right, we're almost there. We got this. Let's see what we can do here. In this first bracket, I've got 4 minus 1, that's 3, and 4 natural log. Well, wait a minute, natural log 1 is 0. So this whole first thing is just 3. 3 minus, over here, I've got 2 minus 2. Oh, well, great, those things just cancel out. So minus 4 natural log 2, and so I get 3 minus 4 natural log 2. Whew. All right, that was a lot to get through. So we've solved this problem. We know how to do integration by substitution for even more complicated things and to do this with definite integrals. You guys are all heroes for getting through this, so bravo to you. As always, if you've got questions, make sure you let me know, and best of luck as you work through the assignment.